she developed a love for computational chemistry or for computational things in general. After her studies, I think she spent some time in Germany on a prestigious Alexander von Humboldt scholarship and joined Stellenbosch University in the year 2000. Yeah. Okay. And today she will give us an overview of her interesting activities in the area of computational chemistry and computational sciences. So, Catharine, thank you very much for being with us today. Thank you.
Thank you so much, and thank you so much for the invitation to be here. It's wonderful to be able to talk about the work that we've been doing in studying intermolecular interactions and the role that they play in a variety of different processes. So I thought, instead of giving you like a flash presentation of hundreds of different things that I've been involved with over the years, I would take you through just a few examples of things that we've done recently that look at intermolecular interactions and the role that they play in material science and so on. But before we do that, I want to take you back a step to where my love for intermolecular interactions first arose. And this was when I was quite young. My mother did this experiment with me where she took a balloon. So this white bit that you see there is a balloon, and it's upside down at the moment. I'll do this. And if you rub a balloon and you put it near a stream of water, you see that the water bends towards the balloon. And what's happening there is that as you rub it, the electrons move to the surface. And then if you've got a water molecule, which looks like this, where you have an oxygen on this side, that oxygen is negatively charged. And the hydrogen atoms are positively charged. And those positive parts of the water molecule then interact with that balloon. And you see the water moves towards the balloon. And of course, I was very little when I learned about this. Later on, I learned about Coulomb's law, and that this was actually an interaction that was a result of this charge distribution. And of course, water is not just a single molecule. There's a bunch of molecules in there. So obviously, what you're seeing there is a lot of different molecules that are in. So we have this interaction here between each of the oxygen atoms and a hydrogen atom that then pull all of these water molecules together. So it's not just a single molecule that moves towards the balloon, but a whole stream of molecules that move. And so these are non-covalent interactions or intermolecular interactions, and the idea being that within molecules you have bonds which are covalent. We call them covalent bonds. But between the molecules, we have these interactions. Sorry, press the right button in the right way. If we have these interactions between molecules. And that's what I find really interesting is if it wasn't for the fact that we had these interactions between molecules, there would just be a bunch of gas molecules floating around. And these then give properties to materials. And this is what we were taught at first year level or even school, that you have these are called hydrogen bonds that are holding the water together, and that gives water its property that it's a liquid. Otherwise, if it wasn't for that, we would have water being a gas. But when you get a little bit further on in your studies, you learn that it's not just about the negative and positive part of the water that is pulling these molecules together. There are other factors that are playing a role. So for instance, we have the reason for this negative charge on the water is the fact that there are electrons, a lone pair of electrons that are on that oxygen. And that lone pair of electrons can actually interact with the water in such a way that the electrons are donated from one water molecule to another. And this is known as charge transfer. It's also called orbital interactions because it's very much like a covalent kind of bond, which involves orbitals, electrons sitting in orbitals. And we also call it a covalent contribution because it looks a bit like a real bond. We call a real bond inside a molecule. There are other factors. These are things that you would have probably learned about at school in science with polarization. So if we have a molecule that has electrons in it, and we bring a positive charge close to that, that molecule, then what ends up happening is the electrons end up being attracted towards that charge, to the positive charge, and that then results in an attraction between the positive charge and the molecule. And that's for where you have a molecule that isn't otherwise polar. In a similar kind of way, we have something called dispersion. This is also London forces, if you remember from your high school days. And there again, we have molecules that may not have an overall charge distribution, but because molecules are made up of electrons moving around nuclei, what can happen is if you've got one electron moving and it comes towards another electron, that second electron is obviously going to be repelled by the first electron because they both have negative charge. And all of those electrons then end up kind of moving together. We call this correlated motion. And what can happen is that as the electrons move, at one instant, we end up with all of the electrons on one side of the molecule. If there are electrons in the neighboring molecule, which there must be, otherwise it wouldn't be a molecule, those electrons are then also repelled by all of these electrons that are in this position at that instant. And we end up getting an overall, in that one instant, we get an overall distribution of electrons that has a positive and a negative charge near each other, and we get attraction. So all molecules, at very least, interact through dispersion. And also all of these factors that we've mentioned here, the electrostatics and all of these, all play a role in our intermolecular interactions. These are attractive forces generally, but we also have repulsive forces, and this is typically called Pauli repulsion. And what we have is we have electrons that cannot be in the same space. Those of you that are physicists will know that this has to do with exchange of electrons. Those of you that are not physicists all you need to remember is that electrons can't, more than two electrons can't be in the same place at the same time. So that results in repulsion. What ends up happening is that we have all of those attractive forces that I mentioned earlier that are lowering the energy as two atoms go from far away. As they get closer, all of these attractive forces that I mentioned are pulling those molecules together, but at the same time we have the Pauli repulsion, which is this line, that is pushing them apart. And at some point we get to a point where two atoms are a distance away, that they are in their lowest possible energy. If we try and force them closer together, then the Pauli repulsion becomes important, and then we get then those molecules are pushed away from each other. And in computational chemistry, what we're trying to do is we're trying to find that point there, because that minimum energy point is where what the molecule would look like if we saw it in nature. And so we're trying to work out what that is. And if we know what the structure of that molecule is at the lowest energy state, then we can start to say things about its properties. And so this is what I'm interested in doing, is finding what a molecule, if you've got two molecules, how do those two molecules fit together? What makes them fit together? Why are they attracted to each other? What is the role of all of these different interactions that I've told you about, the dispersion and all of that? What role does that play in, first of all, the structure here and in their energy? And what can we do with that information in order to try and understand the properties of materials? So I'm going to tell you, as I said, 3 stories, and 2 of them are really sort of applied, looking at the structures of molecules and trying to understand the properties that we're seeing based on the non-covalent interactions. And then I'm also going to tell you a little bit about something more fundamental, is how do all of these, the role of all of these different components of our energy actually play a role in stabilizing systems. So I'm going to start off talking about water. And this is a story that comes back many, many years with a postdoc from Poland who came to work with a colleague of mine, Len Barber, and he's interested in porous materials, so materials that have holes in them. And so she had this material that she knew had pores in it, and she was studying. She brought it from Poland, and she was busy studying it, and she was a little bit confused because sometimes she looked at it and it was yellow, and other times she worked on a different day, she would come in and she would see that it was red. And what is happening is that when there's low relative humidity, so there's not much water in the air, the crystals are yellow. When there's high humidity, the crystals take up water, and you saw a process where we moved the crystals from low humidity to high humidity, and you see that they immediately take up water very, very quickly. And if you look at the time there, that took about less than 2 minutes for the water to fill up this little crystal. It's tiny. I mean, it's less than 1 millimeter long, this crystal. This is seen under a microscope. But what's unusual about this is that crystals that take up water as easily as this one does usually don't lose the water equally easily. And if you do the reverse, so you can, we have videos of the crystal being taken out of the high humidity atmosphere, and it loses the water almost as quickly. And this is very unusual and actually really important, because if you think about applications like water harvesting, so trying to take water out of the atmosphere for drinkable, potable water, you need to be able to get, once you've got the water absorbed into the crystals, into your whatever your water harvesting material is, you need to get it out again. And this is currently an aspect of study that's being very intensively researched, because normally you have to heat it up to quite a high temperature to be able to release the water again. So the fact that this water came out very easily was surprising to us. And we were also quite intrigued by the fact that there was a color change that was associated with the water being taken up into the crystal. So this is when my colleague Len brought me into the study, because this is not something that can be studied experimentally. This is something that you need computational science to explain. But luckily, there was we had a precedent for this. This is the compound that we are working with. We call it trianglamine, and because it's the first one we've worked with, we call it trianglamine 1. You can see it's a triangular shaped molecule, and what's important is this part over here. You can see there's an OH group here, and there's a double bond here. This is an enol-imine functionality. And what happens is that hydrogen forms a hydrogen bond with the nitrogen. This is yellow, and we know that, from previous work that's been done, that what can happen is that hydrogen can shift from there to the nitrogen. That changes the electronic distribution in this ring, and that then changes color. So we were pretty sure that this is what was happening, that the water was interacting then with the OH group here, and that was allowing this hydrogen to move from this side to this side. So we wanted to try and study this. So we brought a master student into this, Dirkie Meiberg, and what he did was he then went and studied these molecules. So there's one of these trianglamine molecules. And what he did was he worked out what the molecular orbitals look like. So when you have a molecule that has electrons in, those electrons aren't just moving around randomly. They move in a specific way according to the orbitals that they are in, and those orbitals are spread across the entire, or can be spread across the entire molecule. And if you have a molecule that has a color, what's actually happening there is the molecules that are sitting in one orbital are being excited by light into a different orbital, a higher energy orbital, and that the light that they are that is being absorbed to the color of the compound is then related to the difference in energy between two orbitals that it's the electrons are moving between. And typically what happens is that they move between one of the highest occupied molecular orbitals, which we call a HOMO, and one of the lowest unoccupied molecular orbitals. So from a full orbital to an empty orbital. And the difference in energy then tells us about the color of the light that's involved. And so this was the idea, is that Dirkie wanted to then study what the orbitals were that were involved in the two different forms. So with the hydrogen bond in different places. And we were very pleased when we saw this, because what this means, this orbital here is then going to be an electron in this orbital here is going to be excited to an electron in this orbital here. And because the orbitals are now, they're located in a very small part of this molecule, it means that he didn't have to calculate what was going on in the whole molecule. He only needed to look at one small part. And computational chemistry is tricky sometimes, in that as you get more atoms in your system, then your calculation starts to become bigger and longer, and it becomes more and more complex. So the fact that he only needed to look at a small part of the molecule made life much easier. So this is what he did. He chopped down that molecule so that it's only got one side, basically. And then what he was doing was he was looking at this. He was saying, okay, we've got this OH group in here. That OH group is going to jump onto the nitrogen. And we're assuming that water molecules are going to stabilize that so that the hydrogen is now attached to the nitrogen. And he wanted to work out if this would ever happen, and if so, how many water molecules would do that. And so he looked at the different cases. So here you can see, so he was looking at molecules where this hydrogen is jumping from here to here. And he found that he could stabilize this oxygen over here without the hydrogen once he had 2 or 3 different molecules. So if this is a positive value, that means that this form is more stable. If it's a negative value, then this form is more stable. So we needed 2 or 3 molecules in order to stabilize this form. And if he calculated this transition from the HOMO, so an occupied molecular orbital, to an unoccupied molecular orbital, he could work out the energy that was involved, and was able to show that the energy of the yellow form only corresponded to, there's a sort of a peak over here which corresponds to a yellow color, but when he looked at this form, he then got a nice red color. And so this, he was able to show then that that indeed it's this transition from the OH hydrogen to the NH hydrogen that changes the color, which is great. So we were absolutely right, and we knew that this had to do with then stabilizing that red color with the water. The problem is that doesn't explain why that color is associated with a very fast uptake. So what you see here is a relative humidity. As it increases, we end, and this is how much water is in this crystal. You can see that until about 55%, there's very little water, and then suddenly there's a big uptake of water, and that is then corresponds to that you saw that sort of red wavefront moving through the molecule or through the crystal. So we know why the color is there, but we didn't understand at that point why that color was associated with this sudden uptake of water. So Dirkie finished, and he decided to move on to other things. And so this stalled for a while until we had a new PhD student, Alan Eby, who decided he wanted to take this on and actually look at why the water is suddenly being taken up at this very high humidity. And so he did some calculations, and what he found was that as he increased the amount of water, so what you can see here is this bunch of these triangular molecules with a channel down the middle. And so this is what the water is moving through. And what you see there is when you have very low humidity, the channels are basically empty, as one would expect. And as we increase the amount of water, what you see is those water molecules sort of stick on these 3 points over here. And those 3 points are OH groups on our on that trianglamine. But not every OH group in a trianglamine is actually involved with this. And I'll show you in a moment that there are some differences. So what's happening here is that at low humidity, the water is interacting with these OH groups, okay? And we can see here the energy of those OH groups is fairly low. So negative here means good. So the more negative, the stronger the interaction. So the first interaction here with the water and these OH groups is a weak interaction. And then as we start getting more and more water, we get to a point here where suddenly we get a very sharp increase in the interaction energy. And what's happening there is all of a sudden, there's enough water in this channel along these, next door to these OH groups, that they operate a bit like a seed for the water interactions. And once there's enough water there, a new water molecule coming in basically can link those two water molecules, and they end up forming these chains of water molecules. And the chains of water molecules are have a much stronger interaction energy, and they then are so it's the formation of chains of water molecules that then result in this very quick uptake of water once you get to a certain point where there's enough water in there that those chains can actually form. And he showed that this was only certain of the OH groups. So there's one OH group, which we labeled number D, which is closer to the inside of the channel, and that's the one that's forming the interaction. The other two that are there don't interact so strongly with the water. And you can see here the water-water interactions are the strongest of all. So he went a little bit further. So he was doing a joint computational and experimental study. So this was the computational. So he was pretty sure he knew what was going on, but wanted to prove it experimentally by getting some crystal structures. And these red dots here are like the red dots in the previous case. They show where water is, or where there's a high probability of finding water. And you can see that it's not very clear what's going on. Now, experimentally, what we can do is we can lower the temperature. And so this is what he was doing, was he lowered the temperature to see if he could kind of freeze the positions of the water molecules, so that he could figure out where they were and what they were doing, and whether what we saw computationally agreed with what he was observing experimentally. And you do see that they do kind of form, there's a sort of a block around the OH groups, and then they form these chains. But it wasn't very clear. It's not a very clear picture because experimentally this is quite hard to do. But while he was doing this, he happened to have the crystal under not very low temperature. So you saw we cooled it down to 100 Kelvin, but he was at minus 60 degrees. And what he noticed was that if he left a crystal at minus 60 degrees like this, you can see it was red, and just at the ends, you start to see a little bit of yellow here. And it's a very long time. You can see there we're at 30 hours already. But if you leave a crystal, even at minus 60 degrees, for long enough, the red crystal goes yellow. And we know that that means that the red crystal had water in it, the yellow crystal does not have water in it. And we were quite surprised. We weren't expecting crystals at minus 60 degrees to lose water. We thought, well, water's frozen in there, and clearly not. And in fact, we were able to prove this computationally as well. So what he did was he filled up computationally. He filled up a channel like this with enough or the same amount of water as we know is in there experimentally from the experiments that I showed you earlier. And then he looked at how much. So he ran some molecular dynamic studies, and he looked at how much the water would move from where it started from over a period of time. And he found that, as one might expect, as temperature increases, the amount that the water moves from its original position increases. So this is at higher temperature, and as the temperature goes down, the amount that it moves decreases. And you can see that even at fairly low temperatures, there is still a certain amount of evidence that the water is actually moving inside the channel, even at these very low temperatures, which we were quite surprised by. And he was able to take this information. So the gradient of these lines is not just a random thing, it's actually the diffusion coefficient. So he was able to get the diffusion coefficient of the water inside the channel in this crystal, and was able to plot it versus temperature. And you can see that diffusion definitely continues until it's very, very small, but it continues until fairly low temperatures. And as I say, we were surprised by this, but when we went and did some reading, we found that actually zeolites do this as well. Not to these low temperatures, but they're down to about minus 30, minus 35 degrees Celsius. You do get diffusion of water through zeolites, okay? But you don't get, or we had never seen anybody talking about the fact that you get water that is leaving the channel. So desorption of water out of the channel had never been reported before. And as I said to you earlier, when you've got water harvesting, this is really important to be able to remove the water from the channel at low temperatures. And typically when they talk about water harvesting, desorption, removing the water from the channels, if it's 30 degrees, plus 30 degrees, like a little bit above room temperature, you've done well. You know, that's really considered ultra low temperature. So to be able to remove water at minus 60 degrees, minus 70 degrees is something remarkable. So we had a little bit of a look, and we did some experimental studies. So this is looking at how the water is removed from a channel. And we realized that the water in that channel is related, or the amount of water in the channel is related to a concentration. And if you know concentration and how concentration changes with time, then you're actually looking at kinetics. So we were able to work out the kinetics of this process. And from that, we were able to work out at what point this desorption of water would actually stop. And we reckon that it stops at around about minus 70 degrees Celsius. That's what the computational results tell us a little bit lower, but experimentally it's around about minus 70 degrees. And the activation energy is typical for any kind of process where you have desorption of water. So everything fits in with what we know experimentally and computationally. Now, what's interesting about this is this is looking at the structures from crystallography, and we see that there's a little point around about minus 60, minus 70 degrees, where there's kind of a stiffening of the crystal structure. And we think that what's happening is that the water forms these chains, and these chains have a periodicity. Chains, water molecules have a certain length between different molecules, and those the repeat chain of the water molecules is different to the repeat chain of these OH groups that actually are linking those water molecules. And we think that this is why the water is actually being able to move and come out of the channel even at low temperatures. And we've put together a list of other compounds that we think will do this, that can potentially lose water at really low temperatures. It's just nobody's ever really looked at it because nobody's ever really thought about the fact that water could be lost from a crystal at temperatures as low as -60, -70. Most people think that, well, I certainly did, that water would be frozen at that point, even inside a channel. But we reckon there are other materials that do this. It's just that nobody's noticed it because the color is, nobody's had a one that changes color so beautifully in the process. So if you are interested in water harvesting, please go and have a look at this paper. There's a list of compounds that we think do this, and maybe your compound is in there, and you can go and see whether or not you can get the water out at very low temperatures. Okay, so this is now a very practical example. Let me take you to a little bit more of a fundamental look. And this is to look at interactions involving gold complexes. So I was very happy to see Helgard Robenheimer, who was my co-supervisor for my PhD, and who is the instigator of this work, in the audience. So Helgard, hello, it's nice to see you. And he did some work with Hubert Schmidbauer a number of years ago, where they were looking at gold complexes interacting with hydrogen. And they did a study where they looked at all of the crystal structures that had been published, and it wasn't entirely clear whether or not those gold compounds could form hydrogen bonds. Now, what had been seen before was that if you've got a gold compound, and gold in compounds are typically 1+, so they've got a positive oxidation state, and so if you think back to that picture of the oxygen, or the water with the oxygen that's negatively charged, what we would expect to have happen here is that the positive gold would interact with a negative oxygen. So in other words, we wouldn't have a hydrogen bond, because with a hydrogen bond, you've got the hydrogen pointing towards the gold. And so this was kind of the expectation, but Helgard wasn't convinced. And the reason he wasn't convinced, well, there were a number of reasons. One of them was that there had been some work done by this guy Kryachko, and he'd looked at gold and silver and some other things as well. And if you have an oride ion, so that's gold minus, that gold minus behaves very much like a halide, so chloride or something like that. And chloride ions can interact with water and form a hydrogen bond. So they are a hydrogen bond acceptor. So he showed that these oride ions could also be hydrogen bond acceptors. And what's interesting about gold is gold is relativistic. And because gold is relativistic, it means it is the most electronegative of the transition metals, which means it's comfortable being negatively charged, which is unusual for many transition metals. So he was convinced that if you chose the complexes correctly, that you could then prove that gold could behave as a hydrogen bond acceptor. And so this is what we wanted to do. We wanted to go and see whether gold could be what we would call in chemistry a Lewis base. Could it act as a hydrogen bond acceptor? And so we started off, so this was a very good PhD student, Vladimir Groenewald, who took this forward. And he started off looking at what Kryachko had done. So he had an oride ion, gold minus, and he again proved what Kryachko had shown, that this was able to form a hydrogen bond. So when we say a hydrogen bond, what we mean is we've got the hydrogen then linking these two, the water and the oride ion. And now obviously what we wanted to do is now say, okay, but gold minus, gold or oride is quite difficult to stabilize, whereas gold in chemistry is typically in the form of complex, a compound. And so it has organic groups on it. In the kind of chemistry that I do, we use organic groups on there, which then are going to change the chemistry of that gold center. And so what we try to do, we could also see that this is quite a strong interaction. First of all, by the energy, which, as I said to you, negative energy means it's a strong interaction, and also by the fact that this distance is quite short. So this 0.88 means that if we just had a gold and a hydrogen sitting next door to each other, not interacting, they would be at what we call the sum of the van der Waals radii. So van der Waals radii, basically the outer edge of a molecule. And so anything less than the sum of the van der Waals radii would indicate that there's probably some kind of strong interaction that's pulling those two molecules together. And this is 0.88 of that distance. So in other words, it's implying that this is a fairly strong interaction, which agrees with the strength of the interaction that we see. This is on the strong side of hydrogen bonds. So hydrogen bonds between water are typically around about 8 kilocalories per mole. Computational chemists are a little bit old-fashioned, I beg your pardon. And so this is quite a strong hydrogen bond. So what we were trying to do was basically mimic this gold minus by choosing organic groups that would then form a compound with gold. And CH3 is an electron donating group, and it puts nice electron density onto that gold so that it can then behave in a very similar way to the oride. And indeed, we found that if we did this, we form a hydrogen bond with the water. So the electron density, if we look at the charge on that gold, it's slightly negative. This is a charge of -1, so this is not nearly that much, but that's typical for a compound, that it would not have a full negative charge anyway. And so we felt that we were going in the right direction. And you can see the interaction energy here is almost as low as this, but there's also there's potentially a weak interaction here as well that's further stabilizing that system. What we can also do is we can do a bunch of different analyses of this kind of interaction. So this is what we did here. This is called a atoms and molecules picture. This looks at electron depletion and strengthening. And so we can see where the electrons are moving to. And this is a non-covalent interaction plot. And what this red part here is telling us is that there is some kind of interaction. There's an attractive interaction here between the gold and the hydrogen. And this is typically what we would expect from a hydrogen bond. And if we look at the properties of a point in the middle here, which is called a bond critical point, that tells us about the nature of that interaction. So if we look at that point, we can look at the electron density at a point here in the middle. So this is, if you think about the gold and the hydrogen having higher electron density, then there is a path of electron density between those two atoms. The bond critical point is the lowest point on this highest path of electron density between the two atoms. And so the fact that there's electron density there of this kind of level is very typical of a hydrogen bond. Other hydrogen bonds between water and so on have properties. So this is the Laplacian. So that's the change in that electron density. And we can see that these values are typical for hydrogen bonds. So this is indeed a hydrogen bond in the way that we would think of a hydrogen bond in water. But does it only work for that? Oh, before I get there, so I said to you that we have various components of our interaction, and so we can also go and do an energy decomposition analysis and look at the various components. So the yellow is the Pauli repulsion, blue is electrostatic. These are our orbital, or that's that charge transfer kind of interaction, and the gray is the dispersion. And what we can see here is this is primarily an electrostatic interaction, but there are significant contributions from orbital and interactions and dispersion. And again, this is quite typical for hydrogen bonds. Water, there's a bit more of an electrostatic interaction, but also we see all of these components. So again, this is a typical kind of distribution that we would expect from a normal sort of hydrogen bond. And we can look at other hydrogen bond donors, so HF, HCN, and as the strength of the hydrogen bond, or the ability of the hydrogen bond, the compound to be a hydrogen bond donor, oops, sorry, beg your pardon, I keep pressing the wrong button, sorry. There we go. As the ability of the hydrogen, of the donor to be a hydrogen bond donor decreases, so does the strength of the interaction as we go down here. And what we can do is we can actually go and plot the electron density at that bond critical point, so the one that I just spoke about just now. We can plot that against the interaction energy, and we see that there's a very nice linear relationship for both for the oride ion and for for this complex here, which is called a dimethyl oride. And we then have so as that strength decreases, we can see that the interaction energy and the electron density are related, which helps us then if we want to then go further and look at other things, like for instance this. So these compounds have what's called, these are an N-heterocyclic carbene. So these blue atoms are nitrogens, the rest are carbons. And you can see that there are now two hydrogen bonds. This nitrogen interacts with the oxygen, forming a hydrogen bond there, and then the gold interacts over there, forming a second hydrogen bond. So we've now got two hydrogen bonds. So this value here of the electron, at least of the interaction energy, is a combination of these two things. But knowing this relationship between the bond critical point, the electron density of that bond critical point, allows us to then get an idea of what the strength of that interaction is. And we see that the interaction strength is again quite similar to what we saw before. We can try and break this hydrogen bond by adding a CH3 group on here. That CH3 group still unfortunately forms a much weaker hydrogen bond, but we can see that we still end up getting a hydrogen bond involving the gold. But certainly the second hydrogen bond here helps in stabilizing the overall system that we have. And this is what we have, what's been found typically. In fact, there's been, since we published this work a number of years ago, there have been a lot of experimental studies. People are using this to look at catalysis with gold, and almost always whenever they see a hydrogen bond involving that gold center, it's typically attached to something else. So it's not just a lone water interacting with the system. There is a secondary hydrogen bond or something else there that is stabilizing the system. We know that this has to do with the relativistic effects, because we can look at this in terms of silver and copper, which have a less relativistic behavior, and those don't form the hydrogen bonds in the same way that gold does. And we further proved this by using a computational method that ignores the relativistic effects. And again, we get something where that hydrogen bond is broken like that. So, which is very much like what we saw for the silver. So, okay. I will skip the last thing. I'm just going to quickly talk about the halogen bonding. So I've mentioned hydrogen bonding. Halogen bonding is a very similar thing in terms of where instead of having a hydrogen atom that's interacting with a donor, we have a halogen atom that interacts with a donor. And this has to do with something that's called a sigma hole, which is a positive area on the halogen. And what ends up happening is if you've got things like fluorine, which are electron withdrawing, they pull the electron density from one of the halogens, so in this case, iodine, and that leaves a positive area, positive region on the atom, and this positive region can behave in the same way that the hydrogen can behave, and we can then get an interaction through this halogen, and it's very directional because there's a strong negative charge around that atom, but the positive charge over here can then interact, say, with an oxygen to form a halogen bond rather than a hydrogen bond in this direction. And we could then, so when knowing that the hydrogen bond forms with gold, we could do the same with a halogen bond. And we found then that in this case, if we look at the oride ion, that this then forms a very strong halogen bond. And these little dots here are bond critical points that tell us that it's an extremely strong interaction involving that gold. In fact, the iodine actually breaks as a result of that halogen bond that forms. And we can see from the energy decomposition analysis, so here's the gold, that this molecule is very much, or this interaction is very much bound by orbital interactions, and that it's a better description of this is that it's actually a gold oride, a gold iodide interacting with an I minus. This description here is actually a better description of what's going on. So these halogen bonds are very strong. We know they're a halogen bond and not just kind of an interaction between a gold and a chlorine, because this is sort of it would be a side-on interaction if it was just interacting, the positive charge was interacting with a negative halogen, and it would be sideways like this. The fact that it's linear means that it's forming, the interaction is happening with that positive part of the halogen, and we can work out with complexes what the strength of that interaction is. And again, people are now using this to look at catalysis with iodine. So I am going to skip this last section because I don't have enough time. One more. Okay, so in summary, what I hope I have been able to show you is that we can use intermolecular interactions to study chemical properties. I looked at sorption, and I spoke to you about the water interacting with a porous compound. And this is very important for potential for water harvesting. The bit that I've unfortunately had to skip was about carbon dioxide uptake. We can do the same kind of thing looking at how carbon dioxide can be taken into porous materials through intermolecular interactions involved in the porous compound. And I've told you a little bit about some unexpected interactions. And these unexpected interactions involving the gold, so the gold hydrogen bond and halogen bonding, can then be used to understand catalytic processes. And I haven't spoken to you about the pharmaceutical processes, but this kind of information helps us to understand how compounds that I've told you about actually work in the body as well. Oranophine is a very powerful gold-based drug, and we've also done some studies where we've looked at the interactions between oranophine and various systems in the body, where these interactions really play a role in the way that the drug works. So finally, I just want to say thank you to all of the people who've done the work and have given the money. And thank you again to NITheCS for the invitation to be here and to you for your attention. Thank you.
Yeah, thank you very much, Catherine, for a very nice talk. Are there questions for Catherine? Please.
Thank you very much for the nice talk. Can you elaborate somewhat on agreement or disagreement between simulation results on the one hand and experimental results on the other hand, as far as the aggregation states or phases of water in these nanochannels at subglacial temperatures are concerned? In particular, is a glassy state predicted or observed?
We didn't look into whether or not we would see a glassy state. We just looked at how the molecules would move. But I would expect that there would be some kind of glassy state because we kind of see something experimentally. So yes, you're absolutely right. There is the model that we use probably wasn't ideal for looking at that kind of agreement. So we used can't remember so this was molecular mechanics, so where we describe the molecules as little weights that are connected by springs with various descriptors for the hydrogen bonding and other non-covalent interactions. So they don't describe a lot of that kind of detail absolutely perfectly. So we would probably need to do something a little bit better like DFT to really get down to the absolute details. We were just trying to understand what was actually going on there. Does that answer your question? I'm not sure.
In part, yes. Thank you. Yeah.
There was another question just behind you, and then we can move the... No.
Sorry, thanks for the talk. I have a quick question. You mentioned several times about the relativistic effect. Could you please a little elaborate on it? I didn't exactly get what kind of relativistic effect.
Okay, so what happens is that the gold, the electrons close to the nuclei move very fast. So they move close to the relativistic limit, and that then means that they become obviously heavier, and they move closer to the nucleus. So those electrons are then stabilized. And what that means then is that you can't create energy, so there has to be a certain destabilization. So what ends up is the outer electrons, our valence electrons, then become destabilized, and they move away from the nucleus. And so because they are more diffuse, they then behave slightly differently to what you would expect. So they have a lot of dispersion that is very important for those outer electrons because they are further away from the nucleus than you would expect. And that then leads to a whole range of different properties, including the color. Yeah. Ah, there we go. I like that. I like that.
Christian, you already have the microphone.
Hi, Catherine. Can you determine a kind of correlation length for the water once it forms those structures inside the...
How do you mean by correlation length? You mean like
a orientation of the water molecule, perhaps?
Yes. So so you saw the experimental results. So they do kind of form these. If you think about water as it freezes, it forms those rings. So we do sort of see parts of rings, and this is, we think, is part of the problem, is that it tries to form those rings of hydrogen bonded molecules, but can't quite, because the OH groups that it initially attaches to are at the wrong distance from each other. So it can't form a nice crystal structure inside the channel. But we do see at, as I say, around about -70, you see a sort of a slight stiffening of the crystal structure of the framework. So we think that it almost gets there at around about that point, but not quite.
Next question here, and then I think we also have a question from a participant online, and we can do it maybe after this one. Yeah, please.
So you mentioned about stability of these molecules, and they'll show the number of E, which is as more negative as then it will be more stable. Then you also show this curvature of the electron density distribution. What's the relation between the two?
So we do see I can't quite remember what the number was. Oh, how was that for a good guess? So this is a relationship. So are you talking about the electron? Are you talking about the electrostatic surface potential? Okay. So sorry, I thought you were talking about this. The electrostatic surface potential. So there's also a relationship there. If you look at the maximum value on your electrostatic surface, if you plot the electrostatic potential on an isodensity surface of the electron density, and then you look at the maximum value of that potential on the surface, then you find that there's a relationship between that value and the strength of the interaction. So there's been a lot of studies that have looked at this kind of thing for a whole range of different interactions. So halogen bonding, hydrogen bonding, a lot of other interactions show these relationships. And in fact, this is used quite extensively for understanding if you've got compound A and compound B and you put them together in a solution, what's going to come out? Are you going to get crystals of A? Are you going to get crystals of B? Or are you going to get crystals of AB? And it is related to the value of your electrostatic potential, the maximum value or your minimum value of your electrostatic potential on that isodensity surface. Some very cool work.
Maybe we should give now an opportunity to 2 online participants to ask their questions. And I think Rene ranked them already chronological order. So please just unmute yourself in that order and ask your question, please.
Hi.
Yeah, may I start?
Okay.
Yeah.
You go first.
Yeah.
Okay. Yeah. Thank you so much for your presentation. This is Taye from University of Botswana. Yes. So my question is mainly about your method. So you used Gaussian, and as you know, Gaussian is just one component Hamiltonian we have there. The basis set, I don't see that the basis set is fully relativistic. But as you have already said, it gold.
Yes, we use a pseudo potential. We use a pseudo potential basis set, so that the pseudo potential is relativistic in the gold. Yeah.
Okay, yeah. So as you have already said, gold is heavily relativistic. And its color is also mainly because of relativistic effects. If you just calculate the absorption of gold and silver just for the atoms, definitely Gaussian will tell you that gold is silverish. That is what we know. So is there any attempt to use relativistic Hamiltonians, for example, either a 2-component or a 4-component Hamiltonian? For the 2-component, you have it in the Amsterdam density functional ADF, or for the 4-component, maybe Orca even, so just a 2-component. Is there any attempt to use the relativistic Hamiltonian?
Yes, so the energy decomposition analysis that I showed you is actually done with ADF, and we used Zora, so there's a 0th order relativistic approximation for that, and we get the interaction energies that we get from that are comparable to what we get from Gaussian. I learned to use Gaussian, so I tend to use that as my go-to, but we use ADF as well, exactly for that reason. Yeah.
Mhm.
And if we
Okay.
use this,
The spin
I showed
orbit,
the experiment
the spin.
where we used a different basis set that wasn't relativistic, and
Mhm.
the effect, the hydrogen bond disappeared. If we do the same and we don't use the the Zora, we get exactly the same effect. We've tested that, yeah.
Okay, thank you.
Okay, thank you.
Was a
But
sec-
from the Zora, you use the scalar or the spin orbit? Which one did you use?
Oh, I think we might have used the scalar one. I'll have to check, but I think we used
Okay.
the scalar version, yeah.
Okay, then thank you very much
Yes,
for the.
yeah. Thank you so much. Yeah.
Let's
Thank
move
you.
maybe second participant online who had a question.
Hi, good afternoon. Thank
Good
you so much for your nice talk. I just had a question about that slide that you calculated. You show us the calculated absorption spectra. So you says that your crystal goes from yellow to red upon adsorption of water, or vice versa of desorption. But when I saw your graph, I didn't see this shift, the shift in the absorption spectra, because with changing the color in adsorption spectra, as I know, is correlated to the shift in peak. If you can go back to that slides of,
So
yeah.
what
So
you
here,
see, there's a yellow component. The yellow component, so in the red crystal, so the yellow component only has this one absorption peak. The red one actually still has that to a certain extent, but it has an additional red absorption over here, and that is then much more dominant than
oh, okay.
the yellow. So you see the red, but the yellow is actually also there.
Oh, okay. Right. Okay. Thank you.
Thank you for your question. And maybe one last question in the physical audience. Zurab, the microphone is on the way.
So the question is, how much does this size matter? Could we do this with larger version of the crystals?
Yes. So this is one of the reasons that I was encouraging people to go and have a look and see if they can find other materials, because you're not going to do it with this one. This is incredibly difficult to make and incredibly expensive to make. And we've got milligrams of this, and it takes a lot of effort to get those milligrams. So this is not going to be the material that's going to be the next water harvester. So absolutely, one needs to make this in kilogram quantities. So we're encouraging people to go and look at other materials and see if they can identify these kind of things for those.
Just a very quick second question. Is color changing property, are there other crystals which one can buy in a shop that have similar properties?
So yeah, so there are a whole range of them. That's why we knew where to start looking, is because this has been known. In fact, I had a quick look today. The first time I could see somebody saying this was 1966. So there are a lot of these compounds that do this kind of thing, but there aren't, that we know of, any that are being used as porous material. Well, we've also seen we've got other color changing compounds, but not this particular type of color change. But they must be out there, absolutely.
Okay, if there are no more urgent questions, Catharine, thank you so much for an excellent talk. And